Okay, so René Descartes was correct when he speculated in the 17th century that the stars were objects like the sun, only very far away, or alternatively that the sun is a star, only up close. And so we're going to address the question, what is a star, by looking at in more detail the sun. And we're going to do so by watching this C'est Pas Sorcier video. And I've given you the link here that starts a couple minutes into the video. I actually suggest you watch the whole video, but then you'll probably want to go back and watch it again because they speak very quickly. And at least I find they speak very quickly. And so I've made this little summary here with telling you what they talk about at various times. So when I write this, I mean, starting at 2 minutes and 55 seconds from the start, up until 4 minutes from the start, they're going to talk about the nuclear reactions that convert hydrogen to helium, etc. This link actually here with the t equals 177, that is a link that starts this video right at that time. Of course, you can just navigate starting anywhere, but I deliberately set this one to start at, for 4 minutes. This is 270 seconds is 4.5 minutes, etc. So go ahead and use those to help you navigate. And after you watch a video like this, I'm sure you've watched many videos, and it's like reading a book, though, right? It's good to test yourself at the end to confirm that you've integrated the material. And so I'm going to go through that with you. This also serves to help you see what I think is important in this lecture, or in this video by C'est Pas Sorcier, and what's important for our lecture. So what's the source of energy from the sun? There's a lot of energy coming from the sun. Is it chemical reactions? Like chemical reaction is the source of energy when you burn something, right? If you burn some gas or a piece of paper, you're releasing the chemical energy stored in that substance. Of course, no, that's not what's happening on the sun. It's a nuclear reaction. In particular, it's nuclear fusion. And a nuclear reaction is when you break and form the bonds between the things inside the nucleus of the atom, the protons and the neutrons. So this is fundamentally different than the chemical reactions in which you break and form the chemical bonds between whole atoms. And because the energy levels are much higher in the nucleus, in the bonds stored in these bonds between the protons and neutrons, so the energy released is potentially much higher during a nuclear reaction than in a chemical reaction. So what is the nuclear reaction in the sun that's going on today? It's the fusion of 4 hydrogens to form the nucleus of a helium. So I've written here for the protons, I've written H. It's actually the nucleus of a hydrogen atom. The most common isotope of hydrogen is is just H1, simply a proton in the nucleus. And the most common isotope of helium here is helium-4, and it has 2 protons and 2 neutrons. And this releases a lot of energy, mega electron volts of energy. So millions of electron volts of energy in the form of gamma rays and neutrinos. Maybe I'll just mention that neutrinos are elementary particles that are very light, and they don't interact with matter very strongly. In fact, extremely weakly. They can pass through light years of lead without interacting. So there's millions of them streaming through us right now that were generated in the sun, and they don't harm us because they don't interact with us. Peut-être je le précise en français, les neutrinos sont les particules élémentaires qui interagissent très faiblement avec la matière. Ils sont libérés par le Soleil, et il y a des millions en fait qui passent par nous, mais ils n'ont aucun effet parce qu'ils n'interagissent pas avec nous. So the interesting part of the energy is coming from the gamma rays. La partie intéressante pour nous de l'énergie vient de les rayons gamma qui arrivent finalement dans le soleil du soleil. So I can write this nuclear reaction in a symbolic form here, where we have 4 nuclei of hydrogen 1, the common isotope, reacting via a nuclear reaction to produce 1 helium-4 nucleus plus 2 positrons and 2 neutrinos. The positron is written E plus like the electron, except with a plus to indicate that it has a positive charge, because the positron is the antiparticle of an electron. So it's much like an electron in all respects, except for its electric charge, which is the opposite. It's +1. So en français, le positron, c'est l'antiparticule d'un électron. Il est presque pareil, sauf sa charge électrique est positive au lieu de négatif comme un électron. And that's it. And I thought we could look at this in a little bit more detail here. With the schematic diagram of how this nuclear reaction takes place, because it's actually takes place in several steps. And in fact, I'm only showing you one pathway, the proton-proton chain pathway that generates that generates the helium-4 from hydrogen. So here I have a hydrogen nucleus, which is just a proton, and another one coming together in a little bang here, a nuclear reaction, and out pops a positron and a neutrino, but also, which are with this source of energy here for us. This is not really relevant, as I pointed out. But then we have this product, which is a proton and a neutron, that's my symbol for neutron, stuck together, which is the nucleus of a deuterium atom, an isotope of hydrogen. So exceptionally, we use a different letter for deuterium, even though it's chemically it's similar. It's the same as hydrogen, in that it has the same atomic number, just one proton, but it's a different isotope because it has the neutron bound to it as well. So this deuterium nucleus and another hydrogen nucleus come together in another nuclear reaction, and there's a little bang, and out comes a helium-3 nucleus. So this is another isotope of helium, the less common isotope of helium. And all this is the pathway 1 of the proton-proton chain. And but there are other pathways at this point that can intervene, and I'm or play a role, and I'm only showing you one of them. It's the most common one that's taking place in the sun. And it's just to give you an illustrative idea of how this could work. So in other words, let's not worry about these ones. So in the pathway 1, you can have one of these helium-3 nuclei and another one generated by a similar process coming together, and there's a little bang, a little nuclear reaction, and out pops a hydrogen and a nuclei and another hydrogen nuclei and a helium-4 nuclei. So there you have it. This is the nuclear fusion of hydrogen to helium-4. So it's a little bit complicated, or it involves several steps. Maybe it's worth mentioning that this first step is highly unlikely. These, in other words, the lifetime of a proton in the center of the sun is billions of years. It takes a long time to go through this formation of deuterium. So how does the sun shine then if it's so hard to do this? Well, there are a lot of protons floating around in the center of the sun, and so this reaction has been taking place since the formation of the sun 4.5 billion years ago, and but because it's so slow, this process will continue for billions of years as well. And these latter steps happen much more quickly. Maybe let's go a little bit beyond C'est Pas Sorcier. It's very informative, but it's more for children, so they don't give details like the history, which is more interesting to us who have a broader perspective. So the astrophysicist from England, Sir Arthur Eddington, in the 1920s already, so 100 years ago, he reasoned correctly that it was nuclear reactions in the sun that provides the source of energy for the sun to shine and the other stars. And that's quite remarkable because at that time they hadn't studied nuclear reactions. Of course, that got going in World War II a few years later. But then very quickly, for historical reasons that you're well aware of, the scientists became very interested in nuclear reactions, and not just for bombs, but to understand stars and the sun. And the physicists, many people played a role, but two physicists, theoretical physicists, played a especially important role in understanding the nuclear reactions in the sun. Hans Bethe, from Germany, but working in the United States in the 1930s, he put the pieces of the puzzle together of how these nuclear reactions could power the sun. And George Gamow, from Russia, but working at Princeton in the United States, he also studied these reactions and how quantum mechanical effects are important in allowing these, especially that first step in our reaction here to take place. Gamow also studied the early part of the Big Bang as well. The Big Bang nucleosynthesis that we talked about in lecture 1. So going back to our C'est Pas Sorcier video about the sun. So which temperature is required? What temperature is required to ignite these reactions, or to kick off these fusion reactions in a star? It's quite impressive, right? It's millions of degrees, 10 to 15 million degrees. I'm not sure they clarified what unit they're talking about, but you could ask, what is it in Kelvin, the absolute temperature scale? And the answer is that it doesn't matter, because there's only 173 degrees difference between the zero of the Celsius scale and the absolute temperature scale. In other words, 0 degrees Celsius is plus 273.15 degrees Kelvin. So we should add that to 10 million, but that's negligible, right? It's in there'd be a decimal and 3 zeros, and then 273. So it's utterly negligible. What is the, so it doesn't matter whether we're saying this in Kelvin or degrees Celsius. What is the rate of this nuclear fusion reaction today? There are millions of tons of matter converted to energy every second, they said. And in fact, they were a tiny bit unclear about this. It was La Petite Voix who was saying this, and she was saying there was 4.3 million tons of hydrogen converted into helium, but it's not quite that. There's much more hydrogen converted to helium every second, but it's the conversion of energy into conversion of mass into energy that is happening at this rate. So you could say that the sun is losing this many tons of matter every second, as that matter is converted into energy, and then the energy is emitted from the sun. via the light and these neutrinos. Mostly, there's also particles coming from the sun, but primarily from the radiation, the electromagnetic radiation and the neutrinos. Okay, so the stars go through various phases of their life, and when a star is on the main sequence, that means that it's at the early phase of its life where it's converting hydrogen to helium. And so that's the first phase of its, from its starting to shine to the end of this first phase is the main sequence. And so how long has the sun been on its main sequence? In other words, how many years has the sun shone? And it's shone for 4.5 billion years. So it's been around as long as the solar system, and just a bit longer than the planet Earth, in fact. And there is enough fuel, or more specifically hydrogen, for the sun to continue on the main sequence of burning, or I shouldn't say burning, because it's not a chemical reaction, it's not an oxidation, it's a nuclear fusion. So how much longer can the sun stay on the main sequence? About 5.3 billion years. Yeah, it has more than enough hydrogen to last this time. For reasons we'll discuss later, it transitions off the main sequence in about 5.3 billion years from now. So the sun is about halfway through its main sequence, its phase on the main sequence. We often talk about the size of the sun, and people are a little unclear about this. So let me be specific. If we talk about a linear dimension, like the radius of the sun, or twice that, the diameter, how much bigger is the radius of the sun compared to the radius of the Earth? Well, first of all, the Earth has a radius of 6,371 kilometers. That's the average radius of the Earth, because the Earth isn't quite a sphere; it bulges at the equator. But on average, it has a radius of 6,371 kilometers. So the sun is approximately 100 times as big as the Earth in linear dimension. But careful, because how much larger is the volume of the sun than the Earth? Well, it's going to be 100 times 100 times 100, right? Because there are 3 dimensions to space. So 100 times 100 times 100 gives a million. It's 1,000,000 times bigger. In other words, you could take 1,000,000 Earths and fit them inside the sun. They'd melt, obviously, instantly, because the sun is so hot. But okay, let's continue with it. There was a lot of information in that C'est Pas Sorcier video. Let's continue with the discussion of the mass and composition and the position of the sun in the Milky Way galaxy. So the sun contains almost all the matter all the ordinary matter in the solar system, and that corresponds to exactly how much? 99.9% of all the mass of the solar system is contained in the sun. So the sun got almost all the mass. We're you and me and the other planets and the asteroids and the dust are all just tiny little trace elements compared to the sun. Okay, when discussing distances in the solar system, we use the astronomical unit. It's the distance between which objects? A hint, the two most important objects, the Earth and the sun. And how many kilometers is that? It's not that convenient to use kilometers, but it's good to, or I find it useful to remember that it's 150 million kilometers in one astronomical unit. And okay, let's try and place the solar system inside the Milky Way galaxy. So how far from the solar system to the center of the Milky Way galaxy? It's about 1.6 billion astronomical units. That's not so convenient a unit. I think it's better to use a more fundamental unit for these large distances outside the solar system. It's 25,000 light years from us to the center of the galaxy to the Sagittarius A. Remember, was the supermassive black hole at the center of the galaxy. Okay, the sun is a big ball of what? C'est une grosse boule de gaz, says uniquement de gaz is what Sabine says. And that's true, but it's an ionized gas, right? Because at these high temperatures, millions of degrees in the center of the sun, thousands of degrees near the surface, the sun is ionized. The gas of the sun is ionized. So it's a plasma, and there are, it's mostly hydrogen and helium, like as we saw in the first lecture. The whole universe is mostly, in terms of ordinary matter, it's mostly hydrogen and helium, 3/4 hydrogen and 1/4 helium. But the same is true in our solar system, and so the same is true in the sun. But there are other elements too, right? And these would be, of course, vaporized. So there would be vaporized iron, etc. Okay, so we've talked a lot about the sun as a typical star. Are all the stars like the sun? Well, all the stars that are on the main sequence, so all the stars that are shining and doing that first phase of their life where they convert hydrogen to helium, those are stars a lot like our sun, but they vary in terms of various parameters, and we can summarize that in terms of 5 key parameters. by far the most important is the initial mass of the star, and that determines its life cycle and how quickly it passes through that life cycle. And so then the age is another important parameter. And then we have 2 or 3 other parameters, which are so it's of more minor importance: the initial chemical composition, the rotation, and the magnetic field in the star. These affect its structure as well, but as I say, the mass is by far the most important parameter, because these determine its evolution and its destiny. Let's take a break there.